All right, ready to dive into some physics.
Let's do it.
Today we're tackling those mysterious symbols that can unlock the secrets of the universe.
Equations.
Yes, equations.
Mm-hmm.
We got a ton of sources from you guys.
Yeah, looks like everyone wants to finally decode those formulas.
I know equations can seem intimidating at first, all those symbols and Greek letters, but trust me.
They make sense.
Yeah. Once you understand the language, they really become incredibly powerful tools. Like they can help us understand everything from how a ball flies through the air.
Like the mysteries of black holes.
Exactly. So no more fearing the formulas, right?
Right.
Our mission today is to crack the code. We're not just going to list them out. We're going to really dig in.
We're going to understand what each symbol means, like why they work together the way they do.
Yeah. And the best part is we'll see how these equations actually play out in everyday life.
Yeah, so it's not just some abstract theoretical stuff.
Right. Okay. Looking at the material you all have sent in, there's a lot to unpack here. It's like a physics buffet.
Oh, I like that.
Yeah, with everything from basic concepts of motion to like mind-bending stuff like relativity.
Yeah, and just like any good buffet, we need to start with the fundamentals.
Okay.
Before we even talk about equations, we
Yeah.
need to make sure we're all speaking the same language.
Yeah, I agree.
And that language is the language of units and measurements.
Makes sense. I mean, you can't really talk
Yeah.
about the speed of a car, for example, without agreeing on whether you're using miles per hour.
Or kilometers per second, yeah.
Exactly.
And what really struck me from the sources you sent is just this crazy range of scales that physicists work with. We have this table comparing the sizes and masses of things from electrons
Oh, wow.
all the way up to bacteria.
Okay.
And just to give you an idea, an electron's mass is around 10 to the power of negative 30 kilograms.
That's incredible. I can't even fathom a number that small.
It's mind-bogglingly small.
Yeah. So if physicists are dealing with numbers that are incredibly huge or incredibly tiny, how do they keep it all straight?
That's where units come in. Okay.
A unit is like a standard quantity of measurement, right?
Right.
So for example, for distance, we might use meters or kilometers.
Mhm.
And for time, we use second or hours. The key is to always be super clear about what units you're using.
Right. Yeah, I definitely remember from my, way back when physics classes,
Yeah.
that getting the units right was crucial. Like one wrong unit and your entire calculation could be just thrown off.
Oh, absolutely. And it's not just about getting, the right answer on a test or something.
Right.
Using the wrong units can have really real-world consequences. Like imagine you're building a bridge.
Oh.
Or designing an airplane. If your calculations are even a little bit off because of incorrect units, like it could be disastrous.
Yeah.
Really bad.
Okay. I'm convinced about the importance of units. What other kind of essential concepts do we need to have in our physics toolbox?
Two other big ones are precision and accuracy. People often use these terms interchangeably,
Right. Yeah.
but in physics, they have very distinct meanings. So precision,
Is how close repeated measurements are to each other. Think of it like throwing darts at a dartboard. If your darts are all clustered together, you have high precision.
So if I'm throwing darts and they're all really close together, but I'm consistently missing the bullseye, that's high precision,
That's high precision, yeah.
but low accuracy.
Yes. Perfect analogy. Accuracy is how close a measurement is to the true or accepted value.
Right.
So to be accurate, you need to be hitting that bullseye.
Okay, got it. So we need both precision and accuracy to have reliable measurements in physics. What about significant figures? I remember that term from somewhere.
Significant figure. Oh, yeah. Significant figures, they help us be honest about what we really know from our measurements.
Yeah.
No measuring tool is perfect, right?
No.
So we can only report our results with a certain level of certainty.
Okay.
So, for example, if you measure a table with a ruler marked in centimeters, you might say it's 120 centimeters long. But you can't say for sure if it's 119.8 centimeters.
Right.
Or 120.2 centimeters because your ruler doesn't have that level of detail.
Yeah. It's about acknowledging the limits of our tools, right?
Exactly. Scientists often use scientific notation to make the number of significant figures really clear. In this case, we'd write the length as 1.2 by 102 centimeters, showing we have two significant figures. It might seem nitpicky,
Right.
but trust me, when you're doing complex calculations, especially with really large or small numbers, significant figures can make a big difference.
Yeah, absolutely. Okay, I'm feeling much more confident about like the language of physics now. I think I'm ready to tackle some equations.
All right, let's do.
What's first on the agenda?
Let's start with something we encounter every day, motion. And to describe motion, we need to understand the concepts of speed and velocity.
Okay. I know we often use those words interchangeably, but I have a feeling physics has a more specific definition for each.
You're right. Speed is simply how fast something is moving, you know?
Right.
It only has magnitude,
Yeah.
meaning it tells us like how much, but not in what direction. Velocity, on the other hand, is the rate at which an object changes its position. It's a vector, meaning it has both magnitude and direction.
So if I say a car is traveling at 60 kilometers per hour, that's speed.
Right.
But if I say it's traveling at 60 kilometers per hour north,
That's velocity, yeah.
that's velocity.
The perfect example. And remember our earlier chat about units? Speed and velocity can be measured in different units. The most common are meters per second or kilometers per hour.
Okay.
Yeah.
All right, let's get to the equation part. How do we actually calculate average speed?
The equation for average speed is pretty straightforward. It's the distance traveled divided by the time it took to travel that distance. We can write it as average speed instills distance travel time of travel.
That makes sense. It's like if you drive 100 kilometers in 2 hours, your average speed is 50 kilometers per hour.
Exactly.
Simple enough. But can you give me like a real-world example where this equation actually comes in handy?
One of your sources has a great problem that illustrates this. It talks about a car traveling at 86.4 kilometers, and the driver, they glance out the window for just 3.3 seconds.
Okay, yeah.
The question is, how far does the car travel during that short glance?
Ooh, that's a good one. I'm guilty of taking longer glances than that sometimes.
Me too, probably.
So let's see how that equation helps us figure that out.
First, we need to make sure our units are consistent. So since our time is in seconds, let's convert the speed to meters per second.
Okay.
Then we just plug the values into our equation, and that calculation will show that the car travels a significant distance,
Oh, wow.
even during that short glance.
That's a great reminder to keep your eyes on the road. Even a momentary distraction can have consequences. But how do we visualize motion? Thinking graphs might be useful here.
You're thinking like a physicist. Graphs are super useful for visualizing and analyzing motion. One common type is a position versus time graph.
So time would be on the x-axis and position on the axis, right?
Exactly. And what's cool about this graph is that the slope of the line tells us the velocity of the object.
Oh, okay.
A steep line means the object is moving quickly.
Okay.
A flat line means it's at rest. And a curved line, that means the velocity is changing, either speeding up or slowing down.
So if I see a position versus time graph for a car that's accelerating, the line would get steeper and steeper.
Precisely. And one of your sources has an example of a graph for a train journey. It shows the train starting from rest, speeding up, then slowing down as it approaches a station. It's fascinating how a simple graph can tell like a story about an object's motion.
Yeah, I'm starting to see how powerful those visual tools are. But speaking of motion, there's another pair of terms that I always get mixed up: distance and displacement. What's the difference and how do they relate to all this?
Another great point. Distance is simply the total length of the path traveled, you know. It only has magnitude and doesn't care about direction. Displacement, on the other hand, is the change in position of an object from its starting point to its ending point. It's a vector, meaning it has both magnitude and direction.
So if I walk 10 meters forward and then 10 meters backward, I've covered a distance of 20 meters, but my displacement is 0.
You got it.
Because I ended up back where I started.
And to visualize this, imagine a bee buzzing around, right?
Okay.
It might fly all over the place, covering a considerable distance, but if it returns to its starting point, like its hive, its net displacement is 0.
Okay, that makes sense. So the bee might be a busy bee, but from a physics perspective, it didn't really go anywhere?
Exactly. And this distinction between distance and displacement is really crucial for understanding more complex motion.
This is all making me see motion in a whole new light. Now, we've talked about position versus time graphs, which show us velocity. Are there other types of motion graphs that are useful?
Another important one is the velocity versus time graph. Just like before, time is on the x-axis, but now velocity is on the a-axis. And in this case, the slope of the line tells us the acceleration of the object.
So if the line on a velocity versus time graph is steep, the object is accelerating quickly, right?
Yes.
And a flat line would mean it's moving at a constant velocity.
Exactly. And if the line is curved, that means the object's acceleration is changing. One of your sources mentions a Ferris wheel as an example of how acceleration can change even if the speed is constant.
Okay.
As you go around the Ferris wheel, your speed might stay the same, but your direction is constantly changing, which means you're accelerating.
That's a really cool way to visualize acceleration. It's making me think about all the different ways things move in the world around us. But I have a question. What actually causes changes in motion? I'm guessing forces are involved here.
You're on the right track. Forces are at the heart of why things move the way they do. And to really delve into that, we need to talk about the one and only Sir Isaac Newton.
Oh, yes, the legend himself. I'm ready to hear about Newton's laws of motion. What's the deal with this inertia thing I've heard about?
Okay, Newton's first law of motion states that an object at rest will stay at rest, and an object in motion will stay in motion at a constant velocity.
Okay.
That is, at the same speed and in the same direction, unless acted upon by an outside force. This tendency to resist changes in motion is called inertia.
So if I slide a book across a table, it eventually comes to a stop because of the force of friction acting on it.
Right.
Right. If there were no friction, it would just keep sliding forever.
Exactly. That's inertia in action.
Yeah.
And you know that classic tablecloth trick where someone pulls a tablecloth out from under a bunch of dishes without breaking them?
Oh, yeah, yeah.
That's another great example of inertia. The dishes want to stay at rest.
That trick has always amazed me. Okay, on to Newton's second law. This is where the famous EFA comes in, right?
That's the one. It states that the net force acting on an object is equal to the mass of the object multiplied by its acceleration. We can write it as Fx ma.
Okay, let's break that down. Force F is any push or pull on an object.
Right.
Mass M is a measure of how much matter an object has,
Uh-huh.
which also tells us how much it resists changes in motion, its inertia.
Yes.
And acceleration, A, as we learned earlier, is the rate of change of velocity.
Mm-hmm.
So this equation tells us that if we apply a larger force to an object, it will accelerate more.
Exactly. And it also means that if an object has more mass, it will accelerate less for the same amount of force. Think about pushing a shopping cart versus pushing a car. You'll need a much larger force to get that car moving at the same rate as the shopping cart
Right.
because it has a much larger mass.
It's all starting to make sense. One of your sources talks about calculating the force needed to push a lawnmower. And it's like a perfect real-world example of how this equation comes into play.
Absolutely. And it also highlights how friction plays a crucial role in those everyday situations. You need to apply enough force to overcome the friction between the lawnmower and the ground to get it moving.
All right, bring on Newton's third law. This is the one about action and reaction, right?
You got it. It states that for every action, there is an equal and opposite reaction.
Okay.
This means that whenever one object exerts a force on a second object, the second object exerts a force back on the first object
Right.
that is equal in magnitude but opposite in direction.
So if I foolishly punch a wall,
Oh, no.
the wall exerts an equal and opposite force back on my fist,
Exactly.
which is why it hurts so much.
Yeah. Even seemingly stationary objects have forces acting on them. Imagine a book resting on a table.
Okay.
The book exerts a force on the table due to its weight, the force of gravity pulling it down. And the table exerts an equal and opposite force back up on the book, preventing it from crashing through the table.
My mind is officially blown. These laws are everywhere, governing like every interaction in the universe. But before we dive into more complex motions, there's one more concept we need to grasp: vectors. And I'll be honest, vectors have always been a bit of a headache for me.
Vectors can seem tricky at first, but they're essential because forces like velocity and displacement have both magnitude and direction.
Right.
Yeah.
Okay, so a vector is basically an arrow where the length represents the magnitude
Uh-huh.
and the direction the arrow points represents, well, the direction.
That's a great way to visualize it.
Yeah.
And we can use vectors to represent things like forces.
Okay.
For example, imagine you're pushing a box across the floor.
Oh, yeah.
You could represent the force you're applying with a vector that points in the direction you're pushing
Uh-huh.
and whose length represents how hard you're pushing.
So if I'm pushing the box with a force of 10 newtons to the right, the vector would point to the right and have length that represents 10 newtons.
Exactly. And we can add vectors together to find the net force acting on an object. For example, if you and a friend are both pushing on that box, we can add your force vectors together to find the total force that's moving the box.
I'm starting to see how vectors can be useful, even if they do make my head spin a little.
Yeah.
They're like a visual language for describing forces in motion.
Precisely. And once you understand vectors, you can unlock a whole new level of understanding about how things move and interact in the physical world.
Okay, I'm feeling like we've laid a really solid foundation here. We've covered units, measurements, motion, graphs, forces, Newton's laws, and even those tricky vectors. I'm ready to dive deeper into the world of physics equations. What's next on our agenda?
Now that we've got the basics down, let's dive into some more specific types of motion. Have you ever wondered how we describe the motion of objects moving in circles?
Oh, yeah. Like a planet orbiting a star or a car going around a bend.
Yeah.
I've always found circular motion a bit mysterious.
Yeah.
It feels like there's a constant tug towards the center, but what's actually going on?
That tug you feel is a force,
Okay.
and it's called centripetal force.
Okay.
But to understand that, we first need to grasp the concept of centripetal acceleration.
Okay, so acceleration is involved, even though the speed might be constant.
Exactly. Think of it this way. Even if a car is going around a circular track at a steady 60 kilometers per hour, its direction is constantly changing.
Right.
And any change in velocity, whether it's speed or direction,
Right.
means there's acceleration. In circular motion, this acceleration is always directed towards the center of the circle, which is why we call it centripetal acceleration, meaning center-seeking.
So the car is constantly being nudged towards the center of the circle, even though it never actually moves directly towards it.
That's a great way to put it. And as we learned from Newton's second law, F is mala, any acceleration must be caused by a force.
Right.
So there must be a force responsible for that centripetal acceleration.
Okay.
And that force is, you guessed it, the centripetal force.
So the centripetal force is what's keeping the object moving in a circle,
Yes,
constantly pulling it in towards the center.
precisely. And the cool thing is that the centripetal force can come from different sources,
Okay.
depending on the situation. For a planet orbiting a star, it's gravity providing that inward pull. For a car going around a curve, it's the friction between the tires and the road.
So if the tires lose their grip on the road, like on an icy surface, the car won't be able to make the turn
Yeah,
because the centripetal force is gone.
exactly. Without enough friction to provide the centripetal force, the car will continue moving in a straight line,
Right.
which can lead to it skidding off the road.
That's a great illustration of how these physics concepts play out in real life. But what about the actual equation for centripetal force? I'm starting to get the hang of these formulas.
The equation for centripetal force is Fc equals mv2r.
Okay, let's decipher that.
All right?
Fc represents the centripetal force. M is the mass of the object, V is its velocity, and R is the radius of the circular path. So this is telling us that the force needed to keep an object moving in a circle depends on its mass, how fast it's going, and the size of the circle.
Got it. The equation shows us some interesting relationships. The faster an object is moving, the greater the centripetal force needed to keep it in that circle.
Okay.
The larger the circle, meaning a bigger radius,
Right.
the less force is required for the same speed.
So if a race car is zooming around a tight corner, it needs a much larger centripetal force
Yeah,
than if it was cruising along a gentle curve at the same speed.
exactly. And that's why race cars need those special tires and aerodynamic designs to help them maintain grip and generate enough centripetal force
Right.
to handle those high speeds and tight turns.
I'm starting to feel like I could analyze the physics of a Formula One race now. But let's shift gears a bit. You mentioned earlier that besides units, we need to have a good grasp of energy to understand physics. What exactly is energy, and how does it relate to all this motion and force stuff?
Energy is a fascinating concept.
Mm.
It's the ability to do work, which means the ability to cause change or motion.
Okay.
And there are many different forms of energy: kinetic energy, potential energy, thermal energy, chemical energy, and more.
Okay, that's a lot to unpack. Let's start with kinetic energy. I've heard that term before, but what does it really mean?
Kinetic energy is the energy of motion. Anything that's moving has kinetic energy.
Okay.
The faster it's moving and the more massive it is, the more kinetic energy it has. Think about a bowling ball rolling down the lane. It has a lot more kinetic energy than a feather gently floating in the air.
So a speeding truck has a lot more kinetic energy than a bicycle, even if they're both moving at the same speed, because the truck is much heavier.
That's right. And the equation for kinetic energy, which tells us exactly how much kinetic energy an object has, is Ke equals 12 meter V2.
Okay, Ke stands for kinetic energy.
Yep.
M is the mass of the object, and V is its velocity. So this equation is telling us that kinetic energy is proportional to the square of the velocity.
Exactly. That means that if you double an object's velocity, its kinetic energy increases by a factor of 4.
Oh, wow.
This is why car crashes at high speeds are so much more dangerous than those at low speeds.
Wow, that's a sobering reminder to drive carefully. So we've got kinetic energy, the energy of motion. What about potential energy? How is energy potential?
Potential energy is stored energy.
Okay.
That has the potential to be transformed into other forms of energy, like kinetic energy.
Yeah.
Imagine you're holding a ball above the ground, right?
Okay. Yeah.
It's not moving, so it doesn't have kinetic energy.
Yeah.
But it has the potential to fall,
Right.
and as it falls, that potential energy gets converted into kinetic energy.
So the higher I hold the ball, the more potential energy it has.
Yes,
Because it has a greater distance to fall.
exactly. The type of potential energy we're talking about here is gravitational potential energy,
Okay.
which is the energy an object has due to its position in a gravitational field.
Right.
And the equation for gravitational potential energy is PE equals mgh.
Okay. PE stands for potential energy. M is the mass of the object.
Mhm.
G is the acceleration due to gravity, which
Mhm.
is approximately 9.8 meters on Earth.
Mm-hmm.
And H is the height of the object above a reference point, usually the ground. So this equation tells us that the heavier the object and the higher it is, the more potential energy it has.
You're getting it. And this concept of potential energy isn't limited to gravity. Think about a stretched rubber band.
Hmm.
It has elastic potential energy because
Yeah.
it's been stretched and wants to snap back to its original shape, right?
Right.
That stored energy can be used to launch a paper airplane, for example.
So potential energy is all around us, just kind of hidden in all sorts of objects, just waiting to be unleashed.
You could say that. And the transformations between kinetic and potential energy are happening constantly in the world around us. Think about a roller coaster. As it climbs up a hill, it's gaining potential energy. As it rushes down the hill, that potential energy is converted into kinetic energy.
That's a great example. I'm
Mm.
starting to see energy everywhere. But one thing I've always wondered about is, where does energy come from in the first place? And where does it go when it seems to disappear?
That brings us to one of the most fundamental laws of physics, the law of conservation of energy. This law states that energy cannot be created or destroyed, only transformed from one form to another.
So the total amount of energy in the universe is constant. It's just constantly changing forms.
Exactly. And that's why perpetual motion machines, which are hypothetical machines that could run forever without any energy input, are impossible. They violate this fundamental law.
Okay, that makes sense. So even though it might seem like energy is disappearing, it's actually just being converted into a different form, like heat or sound, that we might not notice as easily.
Precisely. And this principle of energy conservation helps us understand a wide range of phenomena, from the motion of planets to the workings of our own bodies.
I'm starting to appreciate how energy is at the heart of everything in physics. But I have another question. We've talked about forces causing objects to move, but what about machines? How do they help us do work?
Ah, machines! They're fascinating applications of the physics principles we've been discussing. Essentially, machines make work easier by changing the magnitude or direction of the force we apply.
So they don't magically create energy, but they can make it easier to use the energy we have?
Exactly. Think of a simple lever.
Yeah.
It allows you to lift a heavy object by applying a smaller force over a larger distance.
Okay.
The work done is the same, force times distance.
Right.
But the lever lets you spread that work out over a longer time, making it feel easier.
So it's like a trade-off, right? We're not reducing the amount of work needed, but we're making it more manageable by changing the way we apply the force.
You've got it. And this concept is captured by a term called mechanical advantage.
Okay.
Mechanical advantage is the ratio of the output force a machine produces to the input force we apply. A lever, for example, can have a mechanical advantage greater than 1,
Okay.
meaning the output force is larger than the input force.
So a higher mechanical advantage means the machine is stronger.
You could think of it that way. It means the machine is amplifying the force we apply,
Right.
making it easier to lift or move heavy objects.
I'm starting to see all sorts of machines in a new light now, from simple tools like screwdrivers and hammers to complex contraptions like cranes and bulldozers. They're all using physics to our advantage.
That's right. And even the most complex machines are often built from a combination of simpler machines, like levers, pulleys, wheels and axles, and inclined planes.
Okay.
Understanding the physics behind these simple machines helps us understand the workings of all sorts of amazing technologies.
Oh, wow, this is making me realize how deeply physics is intertwined with our everyday lives and the technology that surrounds us. But speaking of technology, I have to ask, are there any limits to what machines can do? Are there any laws of physics that even the cleverest machine can't break?
That's a great question, and it gets to the heart of some really fundamental concepts. As far as we know, the laws of physics, as we currently understand them, are absolute. They apply everywhere in the universe, and there's no known way to get around them.
So no perpetual motion machines or time travel, at least not anytime soon.
Not likely. The laws of thermodynamics, which govern energy and heat,
Right.
pretty much rule out perpetual motion machines. And while time dilation, as predicted by Einstein's theory of relativity, is a real phenomenon, it doesn't allow for us to travel backward in time.
Okay, so even with all our ingenuity, we still have to play by the rules of the universe.
Exactly. But that doesn't mean there isn't still room for incredible advancements in technology. Who knows what amazing things we'll be able to create as we continue to explore and understand the laws of physics.
This has been a mind-expanding journey so far. We've covered motion, forces, energy, and even dipped our toes into the world of machines. But I have to admit, there's a part of me that still feels a bit intimidated by those tiny particles that make up everything around us, the atoms and all the stuff inside them.
I get it. The subatomic world can seem really abstract and mind-boggling, but once we understand the basic building blocks and the forces that govern them, it all starts to make more sense.
All right, I'm ready to delve into the subatomic world. What's the best way to start wrapping our heads around this?
All right, let's take a journey into the heart of matter, the atom.
Okay.
I remember from school that atoms are tiny,
Yeah,
but just how tiny are we talking?
I know, yeah.
Tiny is an understatement. To give you some perspective, a single human hair is about 1,000,000 atoms wide. And these incredibly small atoms are the building blocks of everything we see and touch in the world.
Whoa, that blows my mind. So, if atoms are so tiny, how did we even figure out what they're made of?
It took some clever experiments
Yeah,
and a lot of brilliant minds.
I bet.
One of the key breakthroughs came in the early 1900s with the gold foil experiment,
Okay.
led by Ernest Rutherford. He bombarded a thin sheet of gold foil with alpha particles, which are essentially helium nuclei.
And what happened? Did the alpha particles just pass straight through the gold foil like tiny bullets?
That's what they expected, but the results were surprising. While most of the alpha particles did pass straight through, a small number were deflected at large angles, and some even bounced straight back.
So it's like they were hitting something solid within those seemingly empty atoms.
Exactly. Rutherford concluded that the atom must have a tiny, dense, and positively charged nucleus at its center. Most of the atom is empty space, which explains why most of the alpha particles pass through unimpeded. But those that came close to the nucleus experienced a strong repulsive force and were deflected.
That's amazing. So they discovered the nucleus by essentially shooting tiny projectiles at atoms. But what's inside the nucleus?
The nucleus is home to two types of particles, protons and neutrons. Protons have a positive electric charge, while neutrons are electrically neutral.
Okay, so we have a positively charged nucleus, but I remember that atoms are overall electrically neutral. Where do the negative charges come from?
That's where electrons come into play. Electrons are negatively charged particles that orbit the nucleus, kind of like planets orbiting the sun. But the force holding them in their orbits is electromagnetic attraction rather than gravity.
So the positive charge of the protons in the nucleus is balanced by the negative charge of the orbiting electrons, making the atom overall neutral.
Precisely. And the number of protons in the nucleus determines what element the atom is. For example, all carbon atoms have 6 protons, while all oxygen atoms have 8.
That's why the periodic table is organized by the number of protons, right? It's like the atom's ID card. But if the nucleus is made of all these positively charged protons crammed together, shouldn't they repel each other and cause the nucleus to fly apart? What's holding them together?
That's a great question, and it brings us to one of the fundamental forces of nature, the strong nuclear force.
Okay, is this force even stronger than the electromagnetic force that's responsible for attracting the electrons to the nucleus?
It is. The strong nuclear force is the strongest force we know of, but it only acts over very short distances within the nucleus itself. It's what overcomes the electrostatic repulsion between the protons and binds the protons and neutrons together in the nucleus.
So it's like a superglue for the nucleus, keeping everything from flying apart.
A very apt analogy, but hold on, there's even more to this story. In the 1960s, physicists discovered that protons and neutrons are not fundamental particles. They're made up of even smaller particles called quarks.
Wait, there are particles inside the particles that make up the nucleus. My mind is starting to melt.
The subatomic world is full of surprises. There are 6 types of quarks with quirky names like up, down, charm, strange, top, and bottom. Protons are made of 2 up quarks and 1 down quark, while neutrons are made of 1 up quark and 2 down quarks.
Okay, I'm trying to keep up. So these quarks are held together by another force.
You got it. The force that binds quarks together is called, appropriately enough, the strong force, and it's mediated by particles called gluons, which you can think of as the glue that holds the quarks together.
So we have quarks held together by gluons to form protons and neutrons. Protons and neutrons are held together by the strong nuclear force to form the nucleus, and then electrons are buzzing around the nucleus, held in their orbits by the electromagnetic force. It's like a whole universe inside every atom.
That's a beautiful way to put it. And this incredible tapestry woven from these fundamental particles and forces is what gives rise to all the matter and energy in the universe.
I'm officially mind blown. But I have to ask, are quarks the end of the line? Are they the smallest, most fundamental particles in the universe?
That's a question that physicists are still grappling with. Currently, we consider quarks and leptons, which include electrons and neutrinos, to be fundamental particles, meaning we don't believe they're made of anything smaller.
So, as far as we know, quarks and leptons are the ultimate building blocks of everything around us.
That's the current understanding. But the history of science has taught us that we should always be open to new discoveries. Perhaps one day we'll find that even quarks and leptons are made of something even more fundamental.
I'm starting to see that science is a never-ending journey of exploration and discovery. It's humbling to think about how much we still don't know. But speaking of mysteries, you mentioned earlier that dark matter and dark energy are some of the biggest puzzles facing physicists today. What's the deal with this dark stuff?
Dark matter and dark energy are intriguing because we can't see them directly. We only know they exist because of their gravitational effects on the things we can see, like stars and galaxies.
So they're like invisible cosmic puppet masters, tugging on things from the shadows.
That's a great analogy. Dark matter seems to act like a sort of invisible scaffolding, holding galaxies together, and dark energy is even more mysterious. It seems to be causing the expansion of the universe to accelerate.
Wow, that's mind-boggling. So most of the universe is made up of stuff we can't even see or understand.
That's right. Dark matter and dark energy make up the vast majority of the universe, while the normal matter we're familiar with makes up a tiny fraction.
It's both exciting and a bit unsettling to realize how much we still have to learn about the universe.
It is, both exciting and unsettling. But that's part of what makes physics so fascinating, right?
It really is. It's a constant quest to kind of unravel these mysteries of the universe and understand like our place in this whole grand cosmic scheme.
Exactly.
One final question before we wrap things up.
Yeah.
You mentioned earlier the idea of like a theory of everything
Oh, yeah.
that would unify all the fundamental forces of nature.
Right.
Is that even possible?
That's the holy grail of physics. Currently, we have separate theories that describe gravity,
Okay.
electromagnetism, and the strong and weak nuclear forces.
Right.
But physicists believe there must be a single overarching theory that explains all these forces as different aspects of the same fundamental force.
So it's like physicists are searching for the ultimate equation that would explain the entire universe.
Exactly. It's a quest that has driven physicists for centuries. And while we haven't reached that ultimate theory yet, the search itself has led to incredible breakthroughs in our understanding of the universe.
This has been an incredible deep dive into the world of physics equations. I've learned so much, and I'm feeling both inspired and humbled by the vastness and complexity of the universe. Thank you so much for being our guide on this incredible journey.
It's been my pleasure. And remember, the journey of discovery never ends. Keep exploring, keep questioning, and never lose your sense of wonder about the universe we inhabit.
That's wonderful advice. And to you, our listener, thanks for joining us on this deep dive. We hope you've enjoyed exploring the world of physics equations with us. Until next time, keep those minds curious and those imaginations fired up.